Hello everyone, welcome to Grandis Series. Today in this video, we're going to take a look at the Grandis series and how it leads to the sum of all natural numbers. And then for the second part of this video, I'm going to demonstrate that why using the Grandis series isn't a correct way to prove that the sum of all natural number equals negative 1 over 12, and why this number itself isn't even accurate. So let's take a look. So this is basically the Grandis series. It's a fairly simple series. And so what is this series equals to? Well, it basically has two answers, actually three. The first two are pretty simple to understand, and the last one isn't that easy to get. It depends on how you put the parentheses around them. If you put the parentheses around the terms in this way, and now the series will equals 0 plus 0 plus 0 plus 0, which means it is 0. And then another way to put parentheses around them is to group the second term and the third term together. So this is basically another way of putting the parentheses around them. And now it seems like this is plus 0 plus 0 plus 0 plus 0. So it's 1 plus infinite amount of 0, which means it equals to 1. And now it becomes slightly more interesting because how come a series has two completely different answers? And let me tell you what, there's another one, and this one is even more intriguing. So if we set this series equals to S1, and we use 1 to subtract S1, so what would that become? So this is basically the result. And then if we distribute this negative sign into it, and that will be the final result. And now, if you can see that this thing, doesn't it come back to the Grandis series that's above? Which means 1 minus S1. S1 is the Grandis series, equals S1. Which means 1 equals 2S1. So S1 equals 1/2. So this series can also equals 1/2. And now we have three completely different answers, and each of them seems very logical. So continuing from up here, now we have proof that the Grandis series equals 1/2. And how does this lead to the sum of all natural numbers? We have to take a look at another series. So Grandis series is S1. And if we set another series, S2, S2 is 1 minus 2 plus 3 minus 4 plus 5. So this is S2. In order to figure out what this series equals, we have to still use the Grandis series. And how do we do that? If we double S2, what would that become? Okay, so this is basically the expanded way to write 2 times S2. And now if we regroup those two long terms, we can start to realize something. So let me just copy the first term down. Okay, so this is the first term. And then plus the second term. We don't just put it right at 1 below. If we shift 1 digit to the right, things will become more clear. So if we shift 1 space to the right, that's basically 1 minus 2 plus 3 minus 4 plus 5 minus 6, right? This is after we shift 1 digit from the right. Or if you can think of it in another way, we can put a 0 here to hold up the place. And then if we do this addition, right here, 1 plus 0 is 1. Minus 2 plus 1, that's minus 1. Plus 3 minus 2, plus 1. Minus 4 plus 3, minus 1. And now this becomes the Grandis series again, right? So if we draw the equal sign over here, 2 times S2 equals the Grandis series. And we have proved above that the Grandis series is 1/2, which means 2 times S2 equals 1/2, which means S2 equals 1/4. So it is fair to say that this series, this long term right here, equals 1/4. And now we are even one step closer to prove that the sum of all natural numbers is negative 1 over 12. And how do we do that? So let me write out the sum of all natural numbers together first. So this is the terms of all natural numbers. And now, if we look back at the series that we have above, S2, and we use this series to subtract S2, which is And now if we distribute this negative sign into it, and then we make the addition right here, it's basically 1 minus 1, that's 0. 2 minus negative 2, that's plus 4. 3 minus 3, 0. 4 plus 4, that's 8, right? And then 5, this will be 0. And then 6, that will be 12. Okay, so this will be the final result of it. And now, if we take a close look at this new series right here, isn't this 4 times the sum of all natural numbers? Because 4 is 4 times 1, 8 is 4 times 2, 12 is 4 times 3, and then 4 times 4, 4 times 5, that comes after it. So this sum is basically 4 times the sum of all natural numbers. And if we set the sum of all natural numbers equals S3, and this term would be 4 times S3, right? And then this term, if we remember from above, is S2, right? So S3 minus S2 is 4 times S3, which means negative S2 is 3 times S3, which means that, oh, and also from above, we can know that S2 is 1/4. So negative 1/4 equals 3 times S3. And S3 equals the negative 1/12. So the sum of all natural numbers, S3 right here, equals negative 1/12. And that's the proof of saying that the sum of all natural numbers is negative 1/12. And I'll tell you what, this proof has some defects in it, and it's not absolutely correct. And which part of it is not correct? In order to solve that, we have to look back at the Grandis series. Let me write out the Grandis series again. So this is the Grandis series. And if we put it in the form of x, this will become And now if we plug in negative 1 for x, the first term will be 1, right? And then negative 1 to the first power, that's minus 1. Negative 1 to the second power, that's plus 1. And then minus 1, plus 1, minus 1, plus 1, right? And now it seems that for this geometric series right here, if we plug in negative 1 for x, we will get the Grandis series. But the defined interval, or the radius of convergence, doesn't include negative 1 in it. And what does that really mean? We have to use the ratio test to test which interval of this series is defined. And what is the ratio test? And the result of it, if the result equals L, if L is larger than 1, means the series divergent. If L is smaller than 1, that means that the series is convergent. If L equals 1, it means that the series is inconclusive, which means that we're not sure if it is convergent or divergent. We have to take a look at specific values. And now, why don't we apply this ratio test to the Grandis series that's above? So, what we have is basically xn, and then n has to n plus 1, right? So it's n plus 1 over xn. And this, if we simplify that, this is when n approaches infinity. And now it seems like after we applied the simplification process, what's left in here doesn't really have an n variable for us to plug in, right? Which means that this will become the result of this limit. So this is basically the result. But now it might be a little interesting, because here, what we said above is that the result L has to be larger than 1, smaller than 1, or equals 1. And now it seems like our result is still a variable. It is not a constant. So what should we do for this situation? Be sure to know that a series only has a point of defining it, or only has its certain meaning if it is convergent, which means that we don't really want a divergent series. So keep that in mind. We can simply put that this absolute value of x is smaller than 1, because that is what we want, right? We want the series to be convergent, and we want to know that its radius of convergence, which means on which interval it is convergent. So we have to set that this series, this result, is smaller than 1. And from this, we can know that its radius of convergence is from negative 1 to positive 1. So within this interval, the series is defined, which means that, and if we know from above, right here, the Grandis series appear when we plug in -1. But this result that we have just shown come back to here that -1 is not included in the interval that we have proven, right? That we have proved down there. Okay, so now we have basically proved that the Grandis series diverges when you plug in -1 for it. However, if the Grandis series diverges, if that is a fact, why do people still tend to believe it? This is because when you expand the Grandis series, the defined interval for that expand function actually includes -1 in it. So what I mean by that is, right, so this is basically the function, and then we plug in -1 as a Grandis series, right? Or in other words, how can we put it in another way? We have to use the sum, the formula of calculating the sum of this geometric series, which is, this is basically the formula. A1 is basically the first term of the series, minus over 1 minus q. Q means the quotient, or the common quotient between them. For example, 2, 4, 8, 16. The common quotient between them is 2, right? Because times 2 every time, so q will be 2. And for our series up there, the common quotient between every term is x, right? So we can apply this formula then. The first term is 1, it's always 1, over 1 minus x. So that will be the formula to calculate this geometric sum. So this is another form of writing this whole thing. We can realize that for the terms on the right, as long as x does not equals 1, it is true, right? It is all true. But then we have just calculated that the terms on the right has to be between -1 and 1, which means that the defined interval of the two terms, left and right, are not equal. So if you plug in -1 to calculate the Grandis series, yes, for a term on the right, for a term on the left, it is applicable. But for the term on the right, it is not, because it is not included in the defined interval. And this is also why that use the Grandis series to prove that the sum of all natural numbers equals -112 isn't an accurate proof. Alright, so that's basically it. That's today's video. So next time, if somebody wants to tell you that the sum of all natural numbers is -112, you can stand up and point out that, hey, that is incorrect. So that is the entire proof, or disproof. And thank you for watching this video. I hope I'll see you next time.